Okay. In the last week, we saw the different sources of errors and their corrections. So first, we saw what is meant by layer stacking, and we saw what is meant by true color composite and false color composite. Then I think in this week, professor would have told about the standard false color composite. I hope the explanation would be clear to you by this time. And then we saw what is atmospheric correction, and in the atmospheric correction, we saw this is third session. We are seeing just the recap of the second session. So in the atmospheric correction, we saw what is manual method, how to do manual method in QGIS, and I also demonstrated how to do it with the SCP plugin, where we saw the dark object subtraction. Then we saw what are the satellite product levels that are available. So we saw what is level 1 to level 4. Then we saw what is geometry correction. Then what are the types? We have two types: systematic, non-systematic. And then systematic errors are already corrected, and they will be given to you as a level 1 product to us. And further, if you want to correct the non-systematic errors, we can do the correction by using the georeferencing, where we saw the ground control points and we saw how many number of points are required to correct for a polynomial. Then we saw how to do a spatial interpolation and intensity interpolation. We saw the bilinear interpolation and cubic convolution by using 16 points interpolation. Then finally, I showed you a quick demo of how to do georeferencing. That is the image to map rectification demo. So in this week, we'll be seeing how to do the image interpretation by using different methods. So by image interpretation, we mean we have two different methods. So we can do it visually, or we can do it by means of statistical methods also. So first we'll quickly go through the what are the things that are available in the visual image interpretation. So in the visual image interpretation, when we say just by looking at the image in your system, we can decipher some of the things like location, color or tone, then size of the features, then what is the shape of some of the features, then is there any pattern in which they are arranged, or is there any texture in the image, then how can we make use of the shadow to visualize some of the things, then making use of height, depth, then volume, then we have slope and aspect. So these are the how to say, these are some of the elements for the visual image interpretation. Then we'll see in detail the digital image interpretation and how to process some of the images. So first we'll look at the statistical methods. In this we'll be seeing some of the statistics, how to evaluate them. So we'll be solving some problems. Then how to do the contrast stretching. So I'll be explaining the linear contrast stretching. Then what is pan sharpening and how to do it in QGIS. That is also one of the image enhancement technique. Then we have band ratioing. I think band ratioing is part of the next week. And spatial filtering and the convolution techniques. This we'll cover in this week. So these are the different image interpretation techniques. So moving on to the first, we have two images here. Both are same image but just rotated. So in this, just by looking at the image, now we need to count the number of camels in this particular picture. So in which image do you think it is easier to count? So by looking at, I mean whether is it easy to count the number of shadows, or whether it is easy to count the number of camels, this camel itself.
Camel itself.
Camel itself. Huh?
Huh. bigger objects, no? So
So in this, which one is the actual camel? So this is the actual camel, no? So this white, small white thing is the actual camel.
oh, right. So yes, the
Okay.
shadows are easier. Yes.
So the shadows are easier to count in this particular image. So see, this is how the shadows also play a very important role. So when and while doing some analysis, it's always the interpreter should always have the shadows facing their side, which means this is the correct orientation of the image. This image is the correct orientation, and this is the false orientation. So why I say the shadow should be facing your side is, if I show you the next image. So in this image, which is the correct orientation? Whether this representation is the correct orientation or this representation is the correct orientation? Can somebody guess?
The one on the left is the correct orientation.
Okay. So just now I explained the shadow should be facing your side. So here these are the major shadows, and it should face to your screen. Although this both image look similar, and if you say, you can say this represents a ridge line of the mountain, and if you see the same image like this will represent your valley of the mountain. But the image on the right side is the correct image, um, because the all the shadows are facing your side. If you see here, some shadows are on the opposite side also, so you should always keep the shadows towards your side. So these are the importance of shadows. So next is the color and tone. This we saw in the last week session itself. So first is the true color composite. We have RGB. Then we saw standard FCC. Then we have some other color composites also. For example, NIR, SWIR, and red. This is one of the color composite. Here it is sensitive to water content because we have both NIR and SWIR brand. So water absorbs in this two band ranges, and it will appear black in color. And since we have put red band, we can also detect the ferric ion content in rocks and the soils, because the whenever any rock or soil has ferric content, it will reflect more in the red band of the red band of the uh, EMR spectrum. And we have another band which is SWIR, NIR, and green. So again, SWIR and NIR are sensitive. Just we have interchange, and we brought in the green band here. And this is sensitive to the moisture content, and it can discriminate the different rocks. And urban area or any barren area will appear dark blue or pink in color. So, for example, here I have shown two different tones. So here, whatever is appearing in orange to reddish in color, they have the um, ferric content in the rocks. And here, if you see this particular image, it also has vegetation on its slopes. And if you see, there are different shades of green, which might represent one place is having higher moisture content than the other place, and the shadows are also there. So we need to be a little bit careful when we are interpreting this particular image. As such, by visualization, we cannot say that this area has more moisture or this area has less moisture. We need to do some statistical analysis. That's where the digital image interpretation also comes into play. So next is the texture. So by definition, texture we can define as the characteristic placement and arrangement of repetition in tone or color. So we have different types of texture. So this is one particular image which I have taken from one literature. So this is in a low altitude, and as we move to the right, it is going up and up. So it is captured from different altitudes for the same place. So you can see how the different gray levels put together form some kind of texture. So it is kind of a row cropping, and this is one of the crop. So it is written as corduroy crop. And if you see, different crops have different textures. So by looking at the texture, we can experience the visual image interpreter can say that this particular texture belongs to this particular crop. By that we can just simply say by visualizing itself. And these are created by tonal repetition. So here you have a dark tones, then in the middle you have the light tones of gray. So it is having some it is arranged in some orderly fashion. So here we should note that two features that have similar spectral signatures might have different textures. So if you remember the spectral signature curve, if you put a false color composite of NIR, standard false color composite, everything will be red in color. But how can you by plotting also everything will have a similar spectral signature. But how can you say that this particular signature belongs to this particular crop? So that's where the textures come into play. So we need to make use of both the methods to analyze any of the images. And textures are described by the adjectives like whether it is smooth, we can say whether it is uniform, homogeneous, then intermediate texture, and rough texture we can say by coarse and heterogeneous. And texture is a function of scale. So as you change your scale of the image, which means larger the scale, the coarser will be the texture. So as you take some photograph from very close up to a very far away distance, so the texture will move from coarse to smooth. So that is the role of texture. And here there are some other examples I have put. So here you have different textures. Here you have some wooden logs piled up, and here you have two different types of crops. This has a relatively smooth texture than this particular side, and similarly we can analyze some of the images. Next is the pattern. So here we are talking about arrangement, how they are arranged. So here you can see some aircrafts arranged in some orderly fashion. Here there are some factory silos that are arranged in a curvilinear fashion. And for our application, we can talk about the what is the pattern of our drainage system. This is in with respect to the application in the water resources engineering. And if you have some township, you can also detect some of the textures. And here this is for one particular crop. Here it is a potato crop, and here you have a urban area which is having a radial structure. So this is the pattern. Okay, so I'll stop the image visual image interpretation with this. More detailed explanation is given in this particular textbook, Jensen. You can go through it. So coming to the main part, we'll be seeing the digital image interpretation. So we have statistical methods. So in statistics, we can say it is univariate statistics or bivariate statistics. So univariate statistics, I'll explain what is univariate and bivariate. So first we'll go through the notations. So in the univariate statistics, it is used to check if there are any unusual characteristics in the data. So you have mean, median, mode, minimum, maximum. All these are like univariate statistics. So we can see if our data has any unusual value in it before going for the any calculations. And we can also compute the bivariate statistics to check if there is any correlation between the bands. So if you see your NIR and SWR may be correlated for maybe correlated, or your red band and NIR may be having some correlation. So this increases the redundancy of your data, which means we can eliminate some of these information and reduce the dimension for our analysis. So some common notations which you need to remember. So from now on we'll be seeing in terms of this notation only. So I refers to particular row of the image, J refers to a column, then K is one band, let's say band 1, or L is another band, let's say band 2. So if I say BV of IJK, then it means brightness value in row I, column J. So we are indicating the pixel, and then for K from the K band of the stack, whichever you are making. and this is similarly for L band. Then we can say minimum and maximum value. Then range, we have range of the brightness value, which is the difference between maximum and minimum. Then quantization means what is the number of gray levels, whether it is 2 power 8 or 2 power 16, that information. Then you can mu k and sk are the mean and the standard deviation. Then skew and kurtosis, which means the skewness and the peakedness. Kurtosis means how peaked the data is in a particular band. Then some other coefficients are covariance of KL. So which covariance, variance, covariance. Covariance is when the data is when the data is not independent, and RKL is the correlation between the pixel. That is the correlation coefficient. Okay, so these are some of the notations. Till now, you have any doubts?
No.
Okay.
It's regarding the color composite, right?
Yeah.
So last week you have shown us how to configure that on QGIS, right, application.
Yeah. Yeah.
But for this one, right? What is this? We have a standard FCC and then true color composite and the grayscale, right? For
Yes.
grayscale, right? Theoretically, I have got an idea, but practically, when we are doing how to configure that on the QGIS, that just required to see.
Your grayscale images, sir. Okay.
Right,
So
right,
if you put all the bands in the similar, like you have band one, band red, blue, and green, right?
right.
So if you give the same band to all the three channels, it will appear gray in color. So your red
No, see,
channel also NAR band, blue channel also NAR band, then green channel also NAR band. So if you give like this, it will appear gray in color.
okay, okay. So the bands should be mapped to only one
Yeah,
channel of the.
one particular band. So it will appear gray in color.
So is it? It can be any channel, like blue channel or red channel or
Yeah,
NIR
all
channel.
three channels should have the same band.
Okay,
So then it will appear gray in color.
okay.
Yeah.
Yeah, that got it.
Okay. So we'll go to the univariate statistics. So first is the measure of central tendency. So we have the first thing, mode. I think everyone knows what is mode, which is the whichever digital number that is having the most frequency, that is the mode of the particular image. Then we have a mean, that is arithmetic average, and it is sensitive to the outliers. So if you have some value that is like a very unusual, your average will be affected by this unusual values. And median is the value midway, that is the 50th percentile value, and it is not sensitive to the outliers because it is dependent on the number of um, elements that are present in it. And we have these are the measures of central tendency, and we can see the measures of dispersion as well, how much a particular pixel is varying from its mean. So that is that we can do by different statistics. So first is the range. We have the maximum and the minimum value. So if you take the difference of it, you will get the range. Then you have your variance. So here variance, we are using variance of a sample. We are not using variance of a population. So we are having a denominator as n minus 1. So you should remember this. And then you have the standard deviation, which is the square root of variance. So if you see here, so for a normal distribution, your mean, median, mode, everything is the same. And if I say the data is positively skewed, then your mode is greater than mean, which is greater than your mean is greater than your median, and then mode. So this is the positively skewed distribution. And for negatively skewed distribution, your image histogram will be populated towards the right, so it will be bright, and positively skewed image will appear typically dark in color. And you have multimodal distribution also. You have Here I have shown the bimodal histogram. So you will have two peaks. So by making use of stretching, we can see the characteristics of each of the uh, peak. And then this particular point we call it as a valley. And if you go to microwave remote sensing, you will learn more about the how to make use of this valley and all. And we have uniform distribution also, so all pixels will have the same probability. And skewness is the measure of symmetry of the histogram. So mostly we will not be using the skewness, so we'll be dealing mostly with the variance and standard deviation for now. And so let's move on to the important part, the covariance. So covariance is the spectral measurement of individual pixel may not be independent. So one pixel value and another pixel value, we cannot say they are independent. So they may have some relation between them. And in nature also, they are often correlated. And covariance gives the joint variation of two variables about their common mean. So now we are going to calculate the covariance. So first we need to find out what is the corrected sum of the products. So corrected sum of products is SP of two bands K and L. So we are going to find out what is the mean of K band. We are going to find out what is the mean of L band. And then we have to subtract this mean from each of the pixel. And then we need to multiply it and then take the summation of it. So that will give you the corrected sum of products. And covariance is given by this formula, SP of KL divided by n minus 1. So this is similar to your variance formula itself. So you will get the covariance from this formula. And here is the so when we calculate covariance, we can calculate it for if you have two bands, so you can calculate covariance of 1 1, then covariance of 1 2, then covariance of 2 1, and covariance of 2 2. So you will have four covariance values, and with this you can generate a matrix. So that is what I have represented here. So if I say X is band 1, Y is band 2, and then Z is band 3. So for a 2 by 2 for two bands, you can say the covariance matrix is something like this. So if you take the covariance of 1 1, what will happen is it will be BVIK minus mu k. This also will be the same. And if you multiply, it will become a whole square. So it will be similar to your variance itself. So that is why here they have represented it as variance. And the covariance of XY or YX. So that will be similar. So 1 2 and 2 1 will be the same. It is just the inverse of it. And for a 3 by 3 matrix, so this will be the covariance. Like this we can generate for n number of bands. So here is an example for 4 bands. So your principal diagonal will be the variance of the that particular band, and all the off diagonal elements will be the covariance which we calculate from the previous formula. And 1 2 2 1 1 3 3 1, all this will be equal values, just your position is changing. Is there anyone having doubt on this? Hello.
See, when you form this matrix, everything will be dn values, right?
Yeah, everything
So when,
we will calculate everything with the dn values only.
and this one, right, in the matrix,
Yeah.
for the SS1, SS2, SS3, SS4, what
Yeah.
are these values?
So these are variance of band 1, variance of band 2, variance of band 3, and variance of band 4.
Okay, single dn values value, right?
No,
It's not it's
variance.
not covariance, it's the variance.
It's variance, yeah. Because if you see here, this will be for band 1. So this will be 1 1, then this will be 1, and this will be again 1 1, and this also will be 1. So we can write it as BV of 1 1 minus mu of 1, the whole square, right? So these two will be equal. And if you see the variance formula, it will be this only. So this is your variance formula, right? Normal for single band.
Right.
So that is why your principal diagonal elements are basically your variance, and your off diagonals are your covariance.
Okay.
Okay. And once we calculate the covariance, we need to find out whether do we have any correlation between these two bands or not. So for that we have the correlation coefficients. So it will show you the degree of interrelation between the variables in a manner that is not influenced by the measurement units, which means your correlation coefficient does not have any unit, it is unitless. So we can compare with across different values. And if we square this correlation coefficient, that is, if you take a square of this RKL, we will obtain the coefficient of determination, that is nothing but your R square, which express the proportion of total variation. So, for example, if I say your correlation coefficient is 0.7, your R square will be 0.49. So, what is the meaning of this? So, it is that 49% of total variation in the band L in the sample is accounted for by a linear relationship with the values of the band K. So, which means if you make a straight line, do a linear regression with by plotting so if you plot this is band 1 and this is band 2. So if you plot all the dn values and if you make a linear regression and you can calculate your r square, so which means, and this linear equation will have some equation y is equal to mx plus c. So 49% of the values that I have plotted can be explained by this equation. So they can be expressed as a straight line equation. So that is what this sentence means. And the rest 51% have a higher residue. We cannot explain that. So that's where the strong correlation, weak correlation comes into picture. So we will see by solving one problem. So I want everyone to solve this problem. So take some 5 minutes time. You need to find out what is the covariance matrix. So it is a 2 by 2. It is a 2 by 2 matrix. So you have two bands. These are the dn values, and to calculate the covariance, first you need to find out what is the mean. Then you need to find out what is the variance. Then you need to find out what is the standard deviation, S or sigma. Then you need to find out what is the covariance, and then you find out what is the correlation coefficient. So when after finishing, taking down all these values, just let me know. I'll go to the formula page so that you can see that and then calculate.
I have taken down all values. Thank you.
Yeah. Everyone has taken down all the values. Wait, let me just put it in a single page. I think you can do now. So anyone completed? Yes, mean is 135, mean 2 is 46.4.
So I'm not able to comprehend how to get the SD, sir. Standard deviation. Can you
First,
please help?
yeah, first you can find out the. Did you find the variance?
Yes, sir.
You take the square root of the variance, that will be your standard deviation.
Okay. Thank you, sir.
Yeah. So anyone has any doubt in the how to calculate like steps? So did everyone get the same answer? So my screen is visible, right?
Yes. Can you please show the? Okay.
So first is you can calculate the mean. It is simple arithmetic averaging. Then similarly, this is for band 1 and then this is for band 2. And then variance is your deviation of pixel value from your mean value. So and then you need to take a summation of it and then divide it by n minus 1. So if you calculate that, you will get your variance. And then if you take the square root of your variance, you will get the standard deviation. That is simple. And for covariance, so this value corresponds to your so this is corresponding to your first value. So whatever you have done in the variance, so you take this value and similarly you will have the first value in the variance too, and then you take a product of that and then you make a summation. So it is 165 minus 135. So here also you have 165 minus 135. And then second one is 50. Second, I think, okay. So your second one will be, this is 35 minus 46.4 the whole square. So, and then 165 is the second value minus the mean. And similarly, for the last pixel, it is here it is 145 and 65. So 145 minus mean of first value, 65 minus mean of second value. You take a sum of that and then divide by 4, you will get your covariance. Is there any doubt in this calculation?
So the variance part.
Variance. So variance is this is your first pixel value, that is 130. Then this is the
So
mean.
excuse me, in the numerator that 130 minus 135 whole square means it's I don't it is having square, but in the formula that square is missing. I think.
Square is missing. See, this is a formula for covariance. This particular thing is for covariance, and if I go to the variance, yeah, here it is. Yeah, it is missing.
Yes.
Yeah.
That's why I got 0, so it should not be available.
Okay. Yeah. Thanks for pointing out. So here it is square. Yeah. Okay. So I think everyone is clear with this calculation. So here, okay. Let me move to my screen. Okay. So here you can see the covariance is 135, and then if you calculate the correlation coefficient, it is 0.35, and if you square it, you will get your coefficient of determination, which is nothing but your r square. So you can see from here. So this is for the correlation coefficient. So if it is 0, then we cannot say anything about the data. But if it is -1, we can say it has a negative correlation. So negative correlation is this kind of variation. That is, as the band 1 increases and band 2 also. For a high band value of band 1 and band 2 and the low value of band 1, your mapping is here. And as your band 1 increases and band 2 decreases, it has a negative slope. So that indicates very strong negative correlation. And Similarly, if it is like in this format, it is having a positive correlation. And if it is scattered something like this, so I think our band 1 and band 2 will have something like this kind of a plot. If we plot it in Excel, we can see this kind of scattered points. We cannot say there is no correlation at all. So by this kind of analysis, we can see whether two bands are correlated or not. So we can move on to the next part. So this is related to your linear stretching. So before going to the linear stretching, you should know something about what is meant by lookup table. So lookup table is nothing but you are converting your actual dn values, which is at a different quantization level, to some other value which is in a different quantization level for our purpose to have it to reduce the range of the values and to have a better visualization through some function. So here dn is your pixel values, h is the stretching function. So this can be linear stretch or a non-linear stretch, and this g is your output. So 16146 that is in the 16-bit.
G is what?
G is the output, this value after your enhancement. And here it is 16-bit range, and after the enhancement, after the linear stretching, we are reducing it to 0 to 255, that is 8-bit range. So this is entirely dependent on us. You can also again stretch it to a 16-bit itself, but with a different range. So let's say if your raster histogram has a minimum value between 20,000 to 60,000, and suppose if this is your histogram, so this is 20,000 and this is 60,000. But I don't want, here if you see there is a very low frequency. So this is a very low frequency. I want to cut because the information is very rich in the middle part of the image. So I want to stretch between these two values. So this will be like, let's say 30,000 to 45,000 you are going to stretch it. So we can also stretch in that way, or we can reduce it to 0 to 255 range as in this particular slide. So it is entirely dependent on us. So this is just for your understanding. And we can convert from here to here and then go back from here to here. So you should remember that these values on the left side, these are the actual surface reflectance values which is recorded by the sensor. And whenever we are doing some application, we should always make use of this spectral reflectance value for all our calculation. So once you make any stretching, that spectral information is lost because you are applying some transformation function. You are adding some constant value and then you are changing it to a different range. So you should not use these values for your calculation. You can just use it for a visual representation only. So is there any doubt in this?
Why we are doing this kind of stretch, linear stretch or those things?
So that I will show you shortly. You will see it practically, like what is the implication. Just it is coming up in the next slides.
Thanks.
Yeah. So we have different stretching. So one is the min-max stretching and then standard deviation stretching. So if you see here for a minimum maximum, so we will see what is the minimum value, we will see what is the maximum value, and then we will simply stretch our histograms. So this is the second type of stretching which I showed you. So if I want to cut it off at some other levels in between, so you can take a standard deviation stretching. You calculate your mean and then you find out your variance, you find out your standard deviation. Take one standard deviation from your mean to the left, one standard deviation to the right. So this is plus minus 1 sigma plus 1 sigma, and then you stretch your histogram. That is one kind of stretching. So This kinds of stretching you can apply by making use of mathematical expression. So now, just now somebody asked one question, why we are doing all this stretching. So it is here. So this is the original image. So can you identify the features, the edges, anything? So everything is like similar, right? We cannot differentiate it very clearly.
Yes, yes.
So and then so this is the original histogram. So if you see here, information is in this frequency there are a lot of pixels. So I think that is the black pixels, the water. So there are so many pixels near the zero value. And then if you see the actual information that is lying here. So we can make use of some other methods to differentiate the water body from our land. But what about the details that are present within the land? So for that we need to make use of this particular range of the histogram, and then we need to stretch it. So here we are using minimum maximum stretching. So it is from here to here only. So we will take only this particular value and then stretch it across 0 to 255. So we are getting some other details from this minimum maximum stretching. But if I do plus minus 1 standard deviation stretching, we are getting much more information. So your water body is very distinct, and then you have I think these are some of the urban areas, I guess. So it is all very bright, and then these are very high density areas. And then if you see the little bit grayish color, these are having less density. And this is kind of a wetland, and then you have your water body. So this is the purpose of linear stretching. And once you stretch it, so here it is like so here it is everything in terms of 8-bit only. So everything is between 0 to 255. We are just clipping the images. So here it is between 0 to, let's say, maybe 80 or 90. But here we are increasing that particular range. So everyone clear with this?
Got it.
Yeah. So now I'm going to show a small demo, like how to do linear stretching in QGIS. So this particular formula, this you need not remember for your course purpose, but when we are doing something practical, you should know this particular formula. So stretched dn value is equal to original pixel value minus the minimum value that we desire. So this is something that we fix, the minimum value desired we fix based on the histogram, and then multiplied by maximum value minus minimum value of the stretched histogram. So this is so if you are doing from 16-bit to 8-bit stretch, so this maximum value will be 255, this minimum value will be 0. Or if you are doing a clipped stretching, let's say 20,000 to 45,000. So for that it is a 16-bit range. So this will be 65535, and this will be 0. And then this is the maximum desired value, this range we fix from the image histogram. This whole thing multiplied by, we are giving a AND condition, logical condition. So all of the raster values which are having greater than the minimum desired value, and all the raster values that are less than the maximum desired values, only for this particular pixels your stretching will be applied. So I will quickly show how to do that in QGIS. So I have just opened a new project, and so I'm going to use Landsat 8 level 2 data. So it is atmospherically corrected, and if you see here, SR underscore B3, this means it is a surface reflectance. So it is not radiance, it is reflectance. So I'm going to take the let's say band 5, that is the NIR band of Landsat 8. So this is the NIR band, and this is again near Chennai. So I have just opened that raster file. So once we get that, so we should go to, you can just double click on it to open this dialog box and then go to the information first. So here you can see what is the maximum value. So you should note down those values. So your maximum value is 28040 and your minimum value is 5545. Okay, and then once we have noted down, we should go to this histogram. So I'm clicking histogram and then you can compute the histogram. So you can see, so these are the, so there is more information in this particular range. So what we will do is we will ignore this particular part and then we will try to use this range. So what I am going to do is, so if you keep here, we can see pick minimum value on graph. So I'm clicking this and then I'm going to set it here. So it is around 16,000. So let's say it is 16,000. This is the minimum desired value that we want. And this is the maximum desired value that I'm going to use. So let's say 21,000. So we have taken the minimum desired value, maximum desired value, and then we have taken all the other values as well. Now once we are done, you can close this, then go to raster. So before that, what I'm going to do, I'm just going to rename it just for convenience. So I'm just going to rename SR_BE5. Okay, and then I'm opening raster calculator. So this is the raster calculator. So here we are going to write that particular formula. So first I'm going to set this one first. So this raster value greater than minimum desired and maximum desired. So I'm going to double click on this. So minimum raster value greater than 16,000 and this is the logical AND operator. Again I'm going to double click on this, less than 21,000 and then you should use brackets, be careful with that. So here you can see expression whether it is valid or not valid. If something is not valid, it will show invalid. Then multiplied by your pixel value. So now I'm going to write the first part of the value. So your pixel value will be equal to your this raster value. So it will move from one pixel to another pixel minus minimum desired value is 16,000 multiplied by, I am going to stretch between 255 to 0, that is in the numerator, and denominator is 21,000 minus 16,000. So I think the expression is valid. So everyone understood this particular expression. So if it is not visible, I will just copy it and then show it in the PPT. So this is the second part of the formula and this is the first part of the formula. And then we can save the output. And then I'm going to click OK. It will take some time. So I have zoomed into the Chennai International Airport. So this is the actual NIR band before linear stretching. And if I put the linear stretching, you can see, I think we should have selected some other range. So these edges have become dark. So here you can see this is how the linear stretching works. So if you select the range properly, you can get very clear image enhancement. So this is another. This is some other. Okay, they have taken band one. So this is the original image before the stretching, and after the stretching, you can see the water bodies have become more dark. The edges are prominent, and then your runway strips are clearly visible. So this is how you can play with the ranges and your linear stretching values to enhance your image. So is there any doubt? Okay.
I have one. I have
Yeah.
just one doubt. Like,
Yeah.
what do we exactly interpret after the linear stretching?
So you are just enhancing your contrast of the image. So your actual original image is like very hazy, and then
Right.
you are not able to visualize the edges prominently. So once you stretch it, the details will start appearing.
Okay, understood. Thank you.
Yeah. So next, the second type of stretching is your
And
histogram.
one more thing, you told some edges are prominent like that
Yeah,
in
yeah,
linear stretching.
yeah. So if you see, um, so this is the original image, right? So if I show the this runway edge and this particular, it is not that clear, no, and this water body boundary. So this is the before stretching, and once you stretch it, you can clearly distinguish what is the edge and then what is the boundary.
The resolution difference.
Hello.
Hello.
Yeah.
Due to variation in resolution, that edges become prominent.
Variation in
Means resolution of different areas, those nearby areas.
resolution. What resolution do you mean?
Suppose initially that previous image just showed,
Yeah, this image.
that image, yes, that image is not very clear.
Yeah.
The low resolution, is it low resolution image?
No,
That I
no.
want to say.
It is the same resolution. It is both are Landsat 8 image only. Both are 30-meter resolution. It is just before stretching, and this one is after stretching.
So the resolution is same.
Yeah, resolution is the same. So we are just changing the brightness value in such a way that the edges are visible.
Okay.
Both are of same spatial resolution only. Yeah. So next technique is the histogram equalization. So what this method does is, so if you see the histogram, it will not be equal. Different brightness will have different number of pixels. So let's say if dn number of 10,000 has 50 pixels, then dn of 30,000 has 100 pixels. These are not equal. So what this method does is, it will try to combine all the pixels in such a way that every dn value, every range of dn value will have same number of pixels. So in that way, if this is the original image, your equalized image will be having more contrast than your original. So by this, by without affecting your total contrast, we can enhance our image. So we will see how we are doing it. So this is the histogram equalization, one example. So this is one histogram unequalized image. So here you can see. So from here to here, we have many pixels, but this entire range is empty. So what we are going to do, we are going to distribute the pixels in such a way that all the dn values will have approximately same number of pixels. Exactly same number of pixels is not possible, so that your contrast is enhanced. So this is the image after your equalization. Your shadows and everything, your topography, everything will be like we can clearly distinguish. So to do the histogram equalization, so this is the formula that was shown in the video lectures. So HV, this is what we are going to find out, equal to, we are going to round off it to the nearest integer. We are going to compute what is the cumulative probability minus what is the minimum probability divided by the number of pixels. M into n will give you the number of pixels, and L is the level of quantization. So if it is a 8-bit image, it will be 2 power 8 minus 1. So that is your value of L. So if you see, let's say for example, if your original histogram is something like this, so these are the number of pixels, and then we are going to compute the probability. So we will take sum of all the pixels, and then this will be 790 divided by sum of all the pixels will give you this probability. Similarly, we will find out all the probabilities. Then we are going to add the probability. So 0.2 plus 0.25 plus 0.23 and so on. Then we will get this particular value, this particular function. And then we are going to assign some other range. So if it is from 16-bit to 8-bit, it will be from 0 to 65535 to 0 to 255. That is the transformation function. And then we will apply that transformation function to get your equalized histogram. So this is the original. So this is after equalization. So you can see some values do not have any pixels. So that is how we will also get in our outputs. So now we can, so this was one of the previous year assignment question. So now we will do a manual calculation just to get the hang of it. So like how the histogram equalization works. So we need to find out the histogram equalized value for a dn value of 52. So we need to find out what is the output brightness value that it was mapped to, the lookup value. So to make the calculations easier, I have, so first we'll go through the steps. So to do the histogram equalization, first we need to find out from the given image what are the unique values. And then after finding out the unique values, we need to find the count. So how many pixels each value has. And then we need to make a cumulative count of it. Then we need to find out what is the minimum value. Then we will have the number of pixels. Then we can apply the formula for the selected dn value. So anybody has any doubt in the 4 steps? Okay, we'll move to the, just to ease the calculation, I have found out what is the histogram count. So these are the values, these are the unique values, and this is the count. So we need to find out, okay, I'll put up the formula in this slide so that you can calculate. Not in this slide. So I have calculated the frequency, which is nothing but how many 20s are there, how many 22s are there, and so on. So our value is 52 and we have 4 pixels. So and I have found out what is the cumulative frequency. Now can you just apply and then find out what is the output value. So this cumulative frequency is this summation of these values. And you can take the value of L as 256 here. So anyone got the answer? Yeah, 238 is the correct answer. I think 8.36 is not the correct answer. Okay, I'll say. So once we get the cumulative frequency, we need to find out what is CDF min. So CDF min is the first value that you have, which is nothing but 3. And the CDF of new. So whatever pixel that you are going to calculate, that is new. So 52 is what we are going to calculate. And what is the corresponding CDF of 52? So that will be 60. And then m into n is your number of pixels. So that will be, you can, if you count the number of rows and columns, it will be 8 cross 8. So it is just 8 into 8, that is 64. Or you can also find out from here, this is also 64. So you can find out from here also. It is just the summation of your frequency. So this m into n is 64, and then again you have your CDF min. So this is 2 power 8. We are going to stretch between 0 to 255. So it is 8 bit, so it is 2 power 8. So that will be 60 minus 3 divided by 64 minus 3 into 255. So that will approximately round off to 238. So that is what I have shown here. So I think everyone understood.
Yes.
Yeah. Okay, now we can see how to do the same thing in QGIS. So again, I'm going to load the Landsat 2. This time, let me take the blue band. So this is the I think it has some issue with the clouds. Okay. Okay, let me try band 3. Okay, this also has clouds. Okay, let's, no problem. Okay, now first step is to get the histogram. So we need to, so if you see here, you have 7601 by 7761 number of pixels. So we need to find out what is the count of each of the pixel. So we need to get the histogram information. So for that, we need to go to raster, then miscellaneous, raster information. So if I click this dialog box will open. So to get the histogram as a like in a format in which we can use, we should type in this advanced parameters, additional command inline parameter hyphen HIST. So this will trigger the histogram function in the Python module, and then it will give us the output. So if you see here, let me open it. So this is the output. I have opened it in the browser, or the same information will be displayed here, but it's not visible properly. So I'm going to the browser. So if you come down, you can see here there are 256 intervals from, this is the lower value and this is the upper value, and these are the number of pixels in each particular value. So we need this particular information. So this entire line we need. Okay, I'll copy it from here itself, so it's much easier. And then I'm just going to paste it here. Then we need to use these values. I'm going to separate it up. So I think data, then text to columns, delimited, space. If you give finish, everything will be like separate rows. So I'm just going to transpose it and then paste it here. Okay. And then okay, so these are some of the things which you need to prepare. First is the lower bound, then upper bound, which is nothing but the minimum value, maximum value. Then number of intervals, that is, it is this entire range is divided into 256 bins or buckets. So what I'm going to do, we have a different lower bound and upper bound value. So I'm going to use that. So this is our lower bound and upper bound values. So what I have done is I have taken upper bound minus lower bound divided by 256. So each interval is this much, 90. 90 is the difference between one value and other value. Now we need to, and we are going to stretch it to new lower bound and new upper bound, which is nothing but 0 and 255. These are the values which we will calculate now. So this is the frequency. So our first value will be equal to this plus this value, the bucket size. So that is our first value, and then our second value is going to be the previous value plus the bucket size. So this will be the previous value plus the bucket size. So we are just going to keep increasing until the end. So is this clear? Now what we are going to do, we need to find the total number of pixels. So I am going to sum the frequency column. Just I am going to give auto sum. So this many number of pixels are there. So it is how much? 40 lakh pixels are there. So we are going to use this value. So I'm going to copy it and take it to the top. So we have this much values. Now for finding the probability, it is the frequency divided by total number of pixels. So we are getting the probability value. So we have just calculated this step now. So histogram of probabilities. So we have got that. Next is cumulation. So the first value will be equal to the same. So this is cumulative probability. Second value will be this plus this value. And then we need to do until the end. So if you go to the end, it will be 1. So probability varies from 0 to 1. Now to find out the mapped value, what we are going to do is, this is the range which we are going to use. We are going to multiply our cumulative probability with this difference of 255 minus 0, so that we will get the new value. So cumulative probability multiplied by difference between these two. So we are getting the mapped value. Okay. So here you need to put that absolute sign, so that's why error came. So this is the mapped value, but if you see here, everything is in terms of 0.19, but what we need is, we need it in terms of integer. So equal to round of this value to 0 decimal places, and then we are getting the rounded mapped value. So it varies from 0 to 255. So we have just applied the transformation function. Now we need to find out what is the lower value and upper value. So we are going to, so the lower value will be the same value as this, and your first interval is going to be this value. So which means your lowermost value plus the bucket size. So this is your first bucket, and then for the next value, this is going to be your lower limit, and this is going to be your upper limit. Everyone clear with this step? So this lower value is the lower bound that you got from the histogram information, and this upper value is 2238.87 plus 90.26, that is the upper limit. For the next interval, this will be the lower limit, and this value plus 90.26 will be your upper limit. So and then it will continue, and the new value is the this value. So I'm just going to copy and paste it here. So once we get this, we need to reclassify. So if you have listened to the lecture, in one of the slides, they would have classified, they would have told about different classes. So I think if I remember it correctly, so there was a image, and then um, so there was a image. This part was coast and this part was land, and then everything was blue in color. So here also blue in color, here also blue in color, and then professor would have told because of change in the similar spectral characteristics or mixing of pixels, both are appearing similar in color. So just check that. So we are going to do a
So I think
classification. Yeah,
it's uh, nearby pixels will be get affected, right?
yeah, mixing of pixels. Yes. So if you see, so we need to have more number of classes. So what we call that in GIS as a reclassification. So we are going to reclassify the image. So for that, we need to save it as a in a particular format. So this is your lower bound value, this is your upper bound value, this is the new value. So I'm just going to make use of the same format, and I'm going to just update with my new values. So I'm just copy pasting it here. Okay. And then I need to save this as a CSV file. So file, save as, browse. Then you can go here, save as type, you can select comma delimited. And then I'm just going to update the existing file. So now it is in terms of a CSV file. So I'm just going to close it. So this I will save it. Now if I come to QGIS, for reclassification there is a function r dot reclass. So it is r dot reclass. So if I open it, so we are going to classify this particular image. So here is the table, file containing reclass rules. So I am going to open this, and then I am going to locate the histogram file, the CSV file that I saved. Okay, it is taking it as a text document. Okay, let me quickly change it as a text. So it is taking it as a text file. So I'm just copy pasting it in terms of text file itself. Okay. So I'm going to locate that file now. So this is the text file which I have saved with the classification rules. I'm going to open it, and then you can just run it. Okay, I think there is some error with the classification tool. Okay, there is a different tool, reclassify by layer. So we can make use of this also. So what I'm doing is I'm trying to bring the CSV file that I have saved into the QGIS. So this I have brought it in. So once I bring this layer, you can see reclassify histogram equalization. So this table has come. So how to import a CSV file? So you need to go to open data source manager. Then this is where you need to locate the file. So select open, and then click on the histogram equalization, the file which you saved, and then you just need to give open. So here you have CSV. So this CSV we need to select, and then we are just going to import it as a table only, so no geometry, and then click on add. So you will add the image, and then minimum class value field, that is your lower bound, maximum is your upper bound, and then we are going to map it to new value. And then these ranges are including your minimum value, but excluding your maximum values. So you should select we are going to include the minimum value, and we are going to exclude the maximum value. So your maximum will be taken care by the next interval, and then we can save this file. Let's try with this. And save as type, always give it as a TIF dot TIF. So where is TIF? Yeah, here it is, TIF. I think it did not work. So there is some issue with the maximum value. Okay, I think there is some issue with the template in which we have given the histogram, this table. So your value should ideally vary between 0 to 255 only, but it is not happening. I'll check the algorithm. I'll check the table once. So I have another image. This is not. So this is one of the image which I did for my tutorial during my course. So this is histogram equalized image, and if you see this histogram, so this is how the histogram looks after your histogram stretching. Let me find the original. I don't think I have the original. I think this is the original. Yeah. So this is your original image. So this is the histogram before equalizing, and then once you do this operation which I just demonstrated, so your histogram becomes something like this, and you can see the difference between both the images. So is everyone clear with this?
See, after enhancement, right? So
Yeah,
it just looks like a positive skewed image, right?
yeah, positive skewed image, because we cannot ideally get a equal histogram like what they have mentioned here, because our dn values will depend it will depend upon our dn values. So this is a very small area, so we will not have a wide range of the values, so number of pixels in each bin will be different.
Okay, but based on the theoretical learning, right? What I have understood is both the negative and then positive will not give you the exact what we say is clear image, right? What my understanding is right or not,
Yeah,
I'm not
yeah,
sure.
yes. But once you do the histogram equalization, ideally it should be like equally distributed,
Gaussian, like
not not
extreme Gaussian.
not a Gaussian distribution also. So all this will have same number of pixels. So if it will be like something like this.
Okay,
So this is a negatively skewed image if you see.
right.
Okay. And this you cannot say whether it is a Gaussian distribution or it is a uniform distribution. It will be close to a uniform distribution.
Yeah, uniform distribution.
Yeah, it should be ideally close to a uniform distribution. So that is how the histogram equalization works. I think there is some error with the
In
lookup
case
type.
of negatively skewed, I think we'll get darker image.
Yeah, it will be dark image. Yes. Okay, I'll check why it is not working. I'll let you know in the next week. I think there should be some problem with the heading of the lookup table. I'll find out. Okay. So next type of enhancement is the filtering options. So we have a spatial convolution filtering. So in spatial convolution filtering, there is one parameter which is called as a spatial frequency. So it is just the number of changes in the brightness value per unit distance for any particular part of the image. So for example, if you look at the urban area, it will have a large spatial frequency, which means many pixels will have similar gray levels than your vegetation or any other kind of classes, because we know from our definition by the spectral characteristic behavior of the concrete, it is uniform in almost all the bands. And but if you see your vegetation, each crop will have a different type of spectral signature. If it is and it also varies across density of the crop. So your urban area will have a large spatial frequency than your vegetation. And the convolution filtering, we have different types of masks. So here I have represented, these are the different types of masks which we can we can with which we can work. So 3 by 3, 7 by 7, this will be odd numbered mask and shape can be different. And these are edge filters. So we have different types. So we'll see what are the types briefly.
So urban area has always a large spatial frequency.
Yeah, spatial frequency here means the number of pixels. It will be more or less similar. So if I just quickly show, so I'm zooming it into a urban area. So you can see, right, the kind of gray shades will be almost similar for most of the urban areas. But if I go to different vegetation, so I think here we have mostly one type of vegetation. I think agricultural. I don't think we'll see the difference here. Okay, let me show one more image.
I think dense vegetation looks darker.
Not necessarily dense vegetation looks darker. You will have a difference in the uh, pixel itself. I'll just find out. Yeah, you can see here, right? So if you see here, it is completely vegetation. But if I zoom in closer, you can see some variation in the texture of the vegetation. So that will be prominent when we do some stretching. So here it is linearly stretched with the NIR band. So when I do the linear stretching with NIR band, you can see the difference. So this has one type of gray level, this has another type of gray level. So this difference will be prominent in your vegetation, but this will not come in your urban area, very dense urban area. So that is what we mean by spatial filtering. That is what we mean by the high spatial frequency. Understood? Okay. So in convolution filtering, so we'll be discussing the 3 by 3 filters. So this is the structure of 3 by 3 filter, and you have C1 to C9 coefficients. So to find out the output of the value after applying your filter, it is just a multiplication of C1 and B1 for this particular filter. It is just a linear filter, just for your understanding. And if I say, if I make a low frequency filter, so in a low frequency filter, so we are going to find out what is the brightness value of this particular pixel after applying your filter. So it is we are going to apply low frequency filter for smoothing purpose. So here it is low frequency average filter. So we are just going to compute the average of all the pixels and then find out what is the central pixel value. So this is for low frequency. For high frequency, here it is 2 times your brightness value of this pixel minus your output of the low frequency filter from the previous calculation. So we need to make use of both for a high frequency filter output. And similarly, we have other types of filter. So average filter, just now I explained. So it is a 3 by 3 window, and we are going to move from move like this. So this will be your first calculation window, and then for second calculation window, you will use this window. and then third calculation window. So by doing that, you will get your central pixel value only, and your edges will be left out. And how to fill the values of edges, I think that has been explained in the video lecture itself. And we have a median filter. So it will this average filter is sensitive to the outliers, and median filter is little bit better than your average filter. And then you have your minimum filter, maximum filter, and we have something called as unequal weighted. So we can change the weights of each of these window, and then we can use this kind of filtering also. So this is one of the application. This is a thermal infrared data for Savannah River. So here there is a river. This is the actual river, and from one of the drainage channel, industrial effluent is being discharged. So industrial effluent, usually it will be at a higher temperature than your river water. So here in thermal infrared, you can see this is a higher temperature and this is a lower temperature, and your industrial waste is movement can be tracked. So this is original image, and then when you apply a low frequency filter, so it is smoothened. But in your median filter, you can still look at the edges of the this particular discharge clearly. And if you put a minimum filter, whichever is at a very high temperature, that is clearly prominent, and these edges are now become fuzzy. And if you put a maximum filter, your total extent of this particular discharge is now found. And if you apply the high frequency filter, it is clearly prominent, which is water and which is the industrial effluent, and how it is flowing across the river. And for such kind of edge enhancements, you have different filters. So these are high pass filters that either diminish your edges or it can sharpen your edges. So this kind of filters you can use. And there is another type, it is called as embossing. Embossing means it will give you a kind of 3D effect. So this is embossing to the east and this is embossing to the northwest direction. So how we are saying whether it is northwest or east, so this particular value is in the east direction and we are reducing the brightness value, so it will appear little dark, and this value we are increasing by 1. So you will have a gradient from left to right. So this will be dark and this will be light, and it will give a kind of slope effect. And here you have the northwest. So this is your north direction and this is your west direction. So this kind of filter you can use. So if you see the output of the image, so embossing in the east direction, it is showing here the edges, the left hand side edges are dark and the right side edges are relatively brighter, and it gives you a kind of a 3D effect. And in the northwest filter you can see to the right side corner towards your first quadrant you have your 3D effect, and if you do a southwest effect it is completely dark. So what kind of filter you are going to apply will depend on the purpose that you are going to use, purpose of your analysis. And similarly, this is Roberts filter and Sobel filter. I think this was also explained in the video lecture. So this is the kind of filter that you will move across your image. So your Sobel filter, this is for X direction and this is in the Y direction. Similarly for Robert filter, X direction and Y direction. And the output of your Sobel filter and the Robert filter is shown here. So you can clearly track the edges, edge map, and then here you can see the difference of temperature. This is at a higher temperature, this is at a lower temperature. In the middle it is at a this is high temperature, and both the edges are at high temperature and the middle is at a lower temperature. So this kind of details was not visible in your median filter or any other filter, but in your Sobel filter it is visible. And in the Roberts filter we cannot see much detail. So these are different kinds of filter. So everyone understood? Like the application part of the convolution filtering.
One question.
Yeah.
When can you please go back to Sobel filters matrix?
Yeah.
So this is a standard Sobel filter.
Yeah,
So
this
when
is
we
a
have,
standard Sobel filter. Yeah.
so see, when we wanted to apply this Sobel filter on the image pixels, right? Original image pixel.
Yeah.
So and we wanted to filter it. It means that we need to reduce or add from the DN values.
We need to multiply all these all the functions which I have shown. It is everything is multiplication here. So this is the standard calculation that we will make. Only exception in case of high frequency filter and low frequency filter. So for high frequency we need to find this. Low frequency we need to find this output. High frequency we need to find out this output.
Okay, no. I mean, like the ones which you have shown as in the matrix, right? Sobel and then
Yeah.
the
Yeah.
other filter, even that as well.
Yeah, we will be just multiplying. So this will be multiplied with your DN numbers.
Okay. The corresponding pixels has to be
Yeah,
multiplied.
yeah, corresponding pixels has to be multiplied. So these are three types of image enhancement. There is one more image enhancement, that is the pan sharpening. So you would have heard about panchromatic image. So I will explain the purpose of the panchromatic image here. This is also one kind of image enhancement where we will sharpen the image. So the idea is we are going to combine or fuse two images. So one will have a core spectral resolution, let's say 30 meter, and another one will have the fine spatial resolution. So your panchromatic image will have a very fine spatial resolution, let's say 10 meter. Now you are going to fuse these two images and you are going to get your output bands. So this is your multispectral band and this is your pan band, panchromatic. And your output will be 10 meter spatial resolution. So if this is 10 meter and this is 30 meter, output will be 10 meter multispectral band. So with the use of pan band, we can enhance our multispectral bands and get a very clear image as a output. So your panchromatic image is an image across your entire visible spectrum. It is having only one single band. It is just a one single band. It will capture your wavelength from blue to all the way up to your red and near infrared. That much will be the wavelength of the pan image, and they have very high spatial resolution. And we have one method which I will demonstrate now. So it is simple band substitution method, and we have one more method which I am not going into detail because it will be too much for you to understand now. So I'm going to describe the simple band substitution method. So this is one of the output. So this is before pan sharpening and this is after pan sharpening. You can see the drastic difference by fusing the images. So this is how we enhance the sharpness of the image by making use of the panchromatic band. So now I will show you the band substitution method. So what we will do is we have a Iconos satellite product which is having a spatial resolution of 4 meter. That is the multispectral band. It is already very fine, but we will be using the panchromatic band of the Iconos, which is 1 meter resolution, and then we will sharpen our image. So for that, first step is to create a multispectral stack raster. Band 1 to 4 we will make a stack, and input 2 will be your panchromatic, Then we will substitute it to find out what is the to enhance our image. So I will demonstrate that. So if you see here, this is the this is the Iconos metadata. So in the first class, I told different satellite products will have different metadata format. So you can look at the metadata format of this. This will be completely different from the Landsat metadata. So here for every image, your azimuth elevation will be given instead of grouping them together. This is how the Iconos provides your metadata. And then now we have the different bands. So blue, green, NIR, pan and red band. So first I am going to import all the multispectral band. So I've just imported. So you can see here is the pixel size 4 meter by 4 meter. First step is to create a stack. So we are going to build a virtual raster. So I'm going to select blue, green, NIR and red and NIR. So I'm just going to swap these two. So red and NIR. I'm going to give OK. And then place each input into a separate band. And then I'm going to save it. So I'm naming it as MSS stack. So multispectral stack. So you have your multispectral stack. So you have a lot of no data values. So I'm just going to go to transparency, set additional no data value as 0, and then I'm going to apply. So it is not going. Okay, no issues. This no data is not. Because yeah. Okay. Because the previous layer were on, so it was not showing. So I'm just going to put the Google satellite. So you can see this is again somewhere south Tamil Nadu. So now we made the stack of your multispectral band. Now I'm going to bring in your pan image. So I'm unchecking this. So I'm going to remove the transparency for this also. No data value as 0. So it just went. So you can see the level of details. So this is one of the buildings. And you can see the same building in the stack also. You can see the difference, right? So it's a very high resolution. So once we do that, here we have a toolbox, processing toolbox. Here I'm going to type pan sharpening. So here you have the tool, pan sharpening tool. So your spectral, you have two inputs. Spectral data set is your MSS stack, and pan chromatic data set is the pan image. And you just have to run this command. So pan sharpening has been done. So I'll just put a false color composite for both of the images, so it will be prominently visible. So band 4 is NIR, 3 was red, and 2 was green. So this is your multispectral So I'm just going to zoom one of the edges. So is it visible? Now I'm going to set the same false color composite for my pan sharpened image. So again that will be band 4, 3 and 2. So is the difference visible? Or let me go to the building. Where is the building? Yeah. So this is your MSS. You are viewing the MSS stack, and then this is the pan sharpening stack. And you can see the resolution of this. The output resolution has become 1 meter resolution. So this is how you can make use of the panchromatic band to enhance your multispectral image, and you can make your analysis. So I hope everyone understood this. Okay. So this is the end of your week 3. So we have seen visual image interpretation, digital image interpretation and processing, then linear stretching. Histogram equalization had some problems. I'll check it out. Then we saw different types of convolution filter, and then we saw a demo on how to do pan sharpening. So in the Google Drive, I have uploaded all the data sets. So this is your week 3 and tutorial data sets. So your first data set is Landsat level 8 surface reflectance for your linear stretching and histogram equalization. Then pan sharpening Iconos data. And then I have shared the Excel files also with you. And then these are the tutorial manuals. You can follow this to get the, you can follow the steps in that. And then so in the last class, I forgot to tell you, in QGIS tutorials file, I have also uploaded the setup file. So you just have to install these two. And these are basics of QGIS. You can start going through in parallel. So I'll share this link. So where to find the previous recordings? Okay. So if you go to your Swayam website, so that is the website. I think everyone would have a login. So in your course catalogs, you can see problem solving session. So if you click on this, it will redirect you to the Excel link. So this is where we will upload all the lectures. So this one is taken by me, and the second one is taken by another TA in tomorrow's evening session. So here you have the YouTube channel link. So I'll share it here as well.
One more thing is uploads, right? Regarding uploads, data uploads, and everything here on the Google Drive.
Yeah,
Even for the previous weeks also will be visible.
yeah.
For us, right?
In every week, if you go to that drive, week 1, week 2, week 3 is there. No, in every week I have uploaded the data.
I mean, like once we get onto that Google Drive, right? Can we see
Yeah.
all the folders week-wise, or like
Yeah, you
each?
can see the folders. You should be able to see this.
Okay, week-wise we can access.
Yeah, week wise you can access. So Google Drive link is also given here. So this is for my session and this is for the other TA session. So this
Okay.
is backup drive link. So you can also download the videos if you want. I have given the access. So I will share all the links here. You can save it somewhere. Okay. If you have any doubts, you can ask me.
Regarding convolution technique, can you discuss some of the advantages and disadvantages?
Advantages and disadvantages. So by making use of convolution techniques, you are basically going to enhance some part of the image which is of importance to you. So one of the application I have just now explained how the convolution filter can help in uh, finding out the industrial discharge into the river. So this is one of the application. So by selectively passing the filter through some portion of the image, we can adjust the contrast in only those particular portions. So we may not adjust in every single place. We can just pass the filter in the place where we are where it is of our interest. So if you say that you are um, you know that there is some industrial discharge that is happening in one of the places, so please clear the concept of BSQ. BSQ is separate files. It is not a single. I'll come to that. I'll just finish explaining this. So if you look at the, so now you know that this part of the image will have some kind of thermal pollution. So what you can do is you can start passing your filter from like something like this. Only in this particular window you can pass your filter, and then you can see what is going to happen. So selectively you are going to adjust what is the contrast of the particular area. So that is one of the advantage of your spatial convolution filtering. And coming to BSQ, I think this has been confusing for everyone for a very long time.
Any disadvantage of it?
Disadvantage, I'm not sure. I think I need to refer it in some of the textbook. I'm not very sure what is the disadvantage. I'll find out. So the BSQ. This is from the week 1. So this is band 1. Then this is band 2. This is band 3. Everything is separate. So if the data is recorded in this way, then it is BSQ. Then BIL. So if you put together everything like this, so this is your band 1 and you join it. This is your band 2. This is your band 3. These are 3 different files. BSQ is 3 different file. BIL is one single file. And this corresponds to band 1 data, this corresponds to band 2 data, and this corresponds to band 3 data. So here it will be line 1, line 2, line 3, so on up to line n. So line by line, you will have different band data. This is BIL. Then band interleaved by pixel. So here what will happen is pixel wise. So this is band 1 pixel 1, band 2 pixel 1, then band 3 pixel 1, then band 1 pixel 2, then band 2 pixel 2, band 2 band 3 pixel 2. So if it is arranged pixel wise, then it is BIP. So this will also be a one single file. So is this clear? In week one quiz, there was
In
a
week one, actually, there was a question.
in week
So,
one. Okay.
yes, we are getting confused.
Just a quick clarification here.
Yeah.
See, uh,